Okay, good afternoon everyone again. So that you pay attention here. We're starting with thermodynamics today. And as you know, till now we've been doing things like states of matter and all, wherein we did talk about the ideal gas law equation. So here, unless and until asked, specified any kind of deviation from the ideal behavior, you will assume your gas to be an ideal one. And so what will be the equation that you will be using? PV is equal to nRT. All of you all make sure that you take care of that. Now because we're starting out with thermodynamics, let me just talk about the basic term first. You know, thermo means heat and dynamics is like anything that is there in motion. I told you there can be two kinds. One can be a static thing and the other is like dynamics. Static is the one which is stationary and dynamic is the one which is like constantly moving. Basically, this idea started by Lavoisier, who proposed that heat is caloric and probably a weightless fluid. Lavoisier stated that heat, basically he started talking about heat, which is also given the term caloric. Generally you talk of the calorific values and all, that's all related to the heat, and that is considered to be a weightless fluid, probably a weightless fluid. And you should be knowing, whenever we talk of fluids, we are talking of gases and liquids. Both of them have the tendency to flow, so that is why gases and liquids both are known as your fluids. They have it's kind of a weightless fluid surrounding the atoms of substances. So basically when we talk about the basic definition of thermodynamics, thermodynamics is nothing but it is like whenever you talk of any kind of heat exchanges between any two systems, right? So when it talks of, it is that branch of science which deals with quantitative relationships. Remember this, that whenever you are going to talk about any kind of quantitative relationships of heat and other forms of energy, of heat, which will be generally represented by this, so you can just put a shortcut here, of heat and other forms of energies. And when you talk about heat and other forms of energies, basically thermodynamics is the branch of science that talks about heat and its relationships with other forms. When we saying quantitative means we are talking about the mathematical relationships. If it is qualitative, it is only by the virtue of understanding. Okay, then what is important here is, what as a part of chemistry we'll be doing is your chemical thermodynamics. You will be taking up chemical thermodynamics as a part of this course. So how is that related? Whenever you talk of the heat exchanges vis-a-vis your chemical reactions are concerned, then you will talk about chemical thermodynamics. Otherwise, general any kind of transformation of heat and its relationship with any other form of energy is thermodynamics. But when you talk about the heat exchanges with respect to your chemical reactions or any chemical change, then you are talking about chemical thermodynamics. Now when you talk about the chemical thermodynamics, there are some advantages or the objectives of thermodynamics. The very first one is, it will help you in predicting the feasibility of the reaction. Alright, so the first kind of purpose is that it will help you in predicting the feasibility. Now what do you understand by feasibility? Whether a particular process will occur or not. So it is also known as the spontaneity of a reaction. Chemical thermodynamics has a very good objective or an advantage, that it helps us in knowing whether a particular chemical process will occur or not, and that is, it will let us know the feasibility of the reaction or whether it is spontaneous or not. A reaction will always occur if it is spontaneous in nature. Remember this, a reaction will only occur if it is spontaneous in nature. Then the next thing is, it also helps us in predicting the yields of the products. Yields of the products means as to how much will be produced in a particular reaction. Like supposedly you started with 10 grams, say it will tell you whether 8 grams or 5 grams or whatever will be produced. So it will predict the yield of the products as well. And not just that, it also helps in deducing some important, some more generalizations of chemistries like your Raoult's law, etc., all can be related to your thermodynamics. Certain important generalization like Raoult's law, you can have different colligative properties like elevation and boiling point, etc., just to name a few. See, wherever you basically, what was your ideal gas law equation? That was PV is equal to nRT. Now let me just tell you that wherever you talk of any kind of heat changes, you will also see that these three variables, pressure, volume and temperature, they will have a good kind of an impact on the heat exchanges. So naturally they all will be linked in some way or the other to the gases vis-a-vis these terms. So wherever these terms are used, it helps to generalize even more formulations using the principles of chemical thermodynamics. Now let's discuss the limitations. Limitations means that there are some kind of not disadvantages, but rather the things which it is not able to do. Like for example, chemical thermodynamics will tell you whether a chemical process will occur or not, but it will not tell you the rate at which it will happen. It will not predict or tell you anything about the rate of the reaction. For the rate of the reaction, there is a separate branch of chemistry which is known as chemical kinetics. You will be doing the rate of the studying about the branch of science that deals with the rates of reactions, that is known as chemical kinetics. So it will not give you any clue about the rate of the reaction, means at which speed the process will occur. Rate will always be in with respect to time. Rate will always be with respect to time. So it will be d by dt of something, right? So whenever you check it with respect to time, your time will always come in the denominator. D by dt, small t is generally used for time, capital T for the temperature. So it will not tell you anything about that, and then it will not talk about anything about the microscopic. It will not take the microscopic properties into account. It will only be talking about the properties in the bulk. That means bulk means macroscopic properties. So it does not link itself to the quantum at all. It only talks about the macroscopic particles. And then it only is related, it is generally dependent upon the states of the system, the initial and the final states generally, and is not interested in the pathway which is, it does not throw any light on the mechanism of the process. Alright, so this is what we are starting up with today. We are going to talk about chemical thermodynamics, and as the name suggests, thermo means heat, dynamics, so some kind of heat changes, right? And when you're going to start talking about the heat changes vis-a-vis your chemical processes, when it is related to the chemical processes, then you talk about the branch of science which is known as chemical thermodynamics. What does it help you in? It helps you in predicting the spontaneity of the reaction, then it yields of the products, and it will tell you about some more laws. It is just to be known, no questions from here generally. Then the limitations, it will tell you nothing about the rate of the reaction. What is the branch of science that talks about the rates of the reaction, right? And what is the branch that decides the spontaneity? Chemical thermodynamics. Then it will not talk about the microscopic properties. So that means your thermodynamics is only talking about macroscopic properties. Macro means it's related to the bulk of the system. Then it will not give you any indication about the mechanism, right? Now there are some important terms which need to be known for thermodynamics. Those important terms are generally summed up as, you can call them the vocabulary of thermodynamics rather. Like it talks about, say, things like, first of all, some important terms which will be used. So let us just jot down the vocabulary of thermodynamics first. In the vocabulary of thermodynamics, the very first thing that we talk about is the system and the surroundings. So whatever portion in the universe that you are studying, say if I am just monitoring this pen, then this pen is my system. Everything else in the universe is my surroundings. Everything else. If I even talk of Pluto now, that's like our surrounding. So it's like everything else around it. Generally our concentration remains around the changes of the system. So the main primary concern is with the system only. So what we have is, one is a system, that is that part of the universe which is chosen for thermodynamic consideration or investigation. Alright, system and surroundings. You should be absolutely clear with that, because now the rest of the things will be related to how things are changing in between the system and the surroundings. So it is very important to understand. I repeat, system is that part of the universe which is under thermodynamic consideration or which is under study. And surroundings is whatever is like left over in the universe is your surrounding. Okay. Then we have different types of systems depending upon how the exchanges are made for energy and matter with the surroundings. One, you have open, closed and isolated. Now an open system is the one in which matter and energy both can be exchanged. Like for example, you talk about a glass which is filled with half with water. Simply it will exchange matter as well as energy, right? And if you heat it, then you can even more better study it, that there will be heat exchanges between it and the surroundings. Then we have, if you just now close the system, this particular system, say you had water in a vessel first, so this is like open system because it is exchanging both matter as well as energy with the surroundings. Now you are taking the same the container to be, say, which is conducting in nature, or generally which is like not an insulator, then in that case you just close it with a lid. So now there will be no exchange of matter, because whatever is there, matter is related to the mass of the substance which is there inside. So whatever is there, mass of the states of matter which is there inside, which may be gaseous, which may be liquid. So there will be no exchange of matter once you close it, but there will be change of energy. So such a system will be known as a closed system. Now if you talk about storing something in an evacuated chamber, so then insulated chamber, then in that case there will be no exchange of energy as well as matter, and then in that case you talk about an isolated system. Alright, then in that case we talk about an isolated system. Then there are other types of systems also. One is a homogeneous system. A homogeneous system is the one in which there is uniformity throughout. It is that system which is said to be uniform throughout. And then you talk about heterogeneous systems. Generally mixture of gases is always homogeneous, or a mixture of completely miscible liquids. If the liquids are completely miscible, or a mixture of a solid which is completely soluble in your liquid. All these cases will give you homogeneous systems. And heterogeneous systems are the ones which are not uniform throughout. So in that case you can talk about a system of two immiscible liquids, you can talk about a mixture of more than one solids, because solids will generally not be miscible with each other at all. So then in that case you can talk about heterogeneous systems, where the entire system is like non-uniform. Immiscible liquids. Okay. Then remember that what we are studying is about the macroscopic properties only. So you should be knowing as to what is the macroscopic properties. They are the ones which are associated with collective behavior of the particles. So we are not now individually focusing on the behavior of any single particle. We've been talking about particles, studying about each and every molecule in specific. Now it is like whatever we are going to do in thermodynamics is like a collective behavior of the particles of the system. So when you aggregate all the microscopic particles together, then that will yield a macroscopic property which will be giving us the results of thermodynamics. So macroscopic properties are the ones which are associated with the collective behavior of particles in a macroscopic system. Then we also talk about collective behavior of various particles in a macroscopic system. Then we also talk about thermodynamic equilibrium. Now, equilibrium is the state in which the rate of the forward reaction is almost equal to the rate of the backward reaction, or you say that the rate of the forward reaction is infinitesimally greater than the rate of the backward reaction, so that such that just a simple force can just revert back the reaction completely. In this also we have different kinds of equilibrium depending upon what you are trying to achieve. You can have thermal equilibrium. Now thermal equilibrium is like when you were mixing, say, a system A, hot water with cold water. Thermal equilibrium will be attained when there is no more flow of heat from one system to another system. Getting the point? You can talk about anything for that matter. Thermal equilibrium is related only to the heat. So when there will be no more heat exchange between, say, A and B, two systems are there, when there is no more flow of heat, you will call it a state of thermal equilibrium. Then you can have a mechanical equilibrium in which no work should be done by one part of the system or the other. Mechanical equilibrium is the state where there is no scope of work to be done on either side. So it becomes equally constant then. Then there is very important one that you will also be doing as a part of your course, that is your chemical equilibrium. Now chemical equilibrium is like when there is no more change in the composition. When a reaction is taking place, when there is no more change in the composition of the system on the left hand side and the right hand side, vis-a-vis your chemical reactions, or when there is no more change in the composition between any two systems that you are talking about. Then in that case you say that the chemical equilibrium is attained. Okay, so that's like one kind of vocabulary, the simple one, and it is very important to know and understand the meaning of each and every term. Let's repeat it again. System is that part of the system which is under study, that part of the universe which is under study. It can be as small or as big as possible. Surroundings, whatever is apart from the system in the existing in the universe, all of that is your surroundings. Now when you talk about systems, there can be different kinds of systems depending upon the exchange of matter and energy. Remember, open is the one in which anything can be exchanged, so both matter and energy can be exchanged. Closed, when it is closed, only energy. Please, there are students who get confused as to what get exchanged. Please remember, when it is closed, matter will just not be able to exchange at all. But I don't know why there is still a confusion when students write that the other way around. I don't even want to speak it up. They write it the other way around. Matter, remember, just cannot get exchanged, and what we have is that we have only energy that gets exchanged in a closed system. So open, both matter and energy. Isolated is also simple, nothing, neither matter nor energy. And when you talk about closed, it's only energy that can get exchanged, not matter. It's like a common sense that matter is related to the mass of the substance. Then we talk about the homogeneous and heterogeneous systems. Remember, a homogeneous system is the one which is uniform throughout. Uniform means that the composition at different stages or the number of molecules at one particular throughout this stage will be like just exactly the same. Here you can talk about the mixture of gases. Gases are completely miscible with one another, so it's like a homogeneous kind of an atmosphere, right? Then you can talk about any two completely miscible liquids. Because if the liquids are completely miscible, again there will be uniformity. Any kind of a solid which is getting dissolved completely, that is also a homogeneous system. Now when we talk about the heterogeneous system is the one which is not uniform. Uniform means it's like the same everywhere, and heterogeneous means it is not the same, not uniform everywhere. So you will find the concentration of the particles to be more in one place than the other within your system. And that can be the case when you have a system of immiscible liquids. Say oil and water are completely immiscible. Now when you talk about oil and water, if you take less of oil and more of water, so then the concentrations will accordingly vary. See, you put 2 drops of oil will be floated on top of water. You put 2 drops of water in oil, you know that it will be the other way around. So the concentration also depends on the compositions then, and it is not uniform. Then even if you have the equal quantities, then also again the denser one will be there below and the lighter one will be above, but the distribution will be non-uniform, and that is why a system of 2 immiscible liquids will be heterogeneous in nature. Or you can talk about any 2 mixture of any 2 solids, that also can be heterogeneous in nature. Then we talk about macroscopic properties. Why? Because here thermodynamics, I just told you while talking about the limitations, it is like talking only about the properties in the bulk. It is not concentrating on each and every particle. So what does the macroscopic properties means? That it is a collective behavior of all the particles in your macroscopic system. So you have this particular classroom as a system, then it is whatever behavior you are studying for the chemical molecules as a part in totality of this macroscopic system will be your macroscopic property. So if you have to talk of the pressure, it will be the total pressure. If you have to talk of the volume, it will be the total volume, which will be summed up for each one of them depending upon how they get added up. Then basically one thing is like every system tries to attain a state of equilibrium, right? So here different types of thermodynamic equilibriums also need to be understood. How here I have given you only 3 types of thermodynamic equilibriums. One is the thermal equilibrium. Thermal means heat. So it is that kind of an equilibrium where no more scope of any heat exchanges is possible. So it is like that means both the systems, say if I am talking about 2 systems A and B, both A and B have attained same temperature. Or I mean if I am talking about heat, you can always relate it to temperature anyways. Yes, you can say that. Okay. Then when we talk about the mechanical equilibrium, in case of mechanical equilibrium there is no scope of any more work that is to be done. That is the state of mechanical equilibrium. When you talk about the chemical equilibrium, we are by and large talking about the chemical processes. So there is no scope of any more changes in the composition. So that means the compositions that are there on either side have become same. Alright, now then we can talk about different types of properties also. For different types of properties, you can have 2 kinds. One is the extensive properties. Extensive properties are those which depend upon the quantity which depend upon the quantity of the matter contained in the system. It depends upon the quantity of the matter, depends on quantity of matter, or in many of the books you will find that extensive properties are those which are dependent upon the mass of the system. Quantity or matter of the system, matter contained in a system. Alright, and for this, if you have to think of the examples, you can have mass, volume, you can even talk about energy, can also talk about heat capacity. Alright, please take a note of this. Extensive properties are those which are dependent upon the quantity of the matter contained in a system. And how do you remember it? The other part of it, the other property that is just opposite to it is like intensive property. And in order to remember it, you can remember the I and I. Intensive properties are independent of the matter. So they are independent of any kind of quantity of matter. Intensive properties are the ones which are independent of matter. Let us take down some examples. Intensive properties can be temperature, you can have temperature, pressure, refractive index, Like you can have viscosity, you can have surface tension, density and specific heat. Etc. You can talk about more. I repeat, extensive properties are the ones which depend upon the mass or the quantity of matter contained in the system. So you have the examples as mass, volume, energy, heat capacity. What is heat capacity? It is the amount of heat required to raise the temperature of a substance by 1 degree Celsius. It is temperature of a substance, so that substance has some mass, right? So it is the amount of heat required to raise the temperature of a substance by 1 degree Celsius. So it is dependent upon the mass of the substance, so it is an extensive property. Now when I talk about specific heat is the amount of heat required to raise the temperature of 1 gram of the substance. So now I am talking about the heat capacity per gram. You getting the point? I repeat, I will give you some more hints as to how to find out, because this question also comes in that this property is intensive, extensive, both or none. Both is not possible. None is again not possible, because your property will either be intensive or it will be extensive. So sometimes you have extensive property depends upon the quantity of matter. Now here heat capacity, I am just giving you a justification. Heat capacity is the amount of heat required to raise the temperature of a substance. कि कितनी हीट चाहिए to raise the temperature of a substance. So that substance has some mass by 1 degree Celsius. So it will be dependent upon how much of substance are you giving. I give you this much, you may require less heat. I give you this much, you may require more heat. But if I am asking you the amount of heat required to raise the temperature of 1 gram of the substance, so that is independent of mass, because I am specifying now per gram. And to understand it in another way, heat capacity is for a particular mass by grams, because it is per gram, so gram by gram will get cancelled and it becomes independent of matter. So then in that case your specific heat will come in the category of intensive property. What are the other intensive? Molar heat capacity will also be per mole, so it can also be worked out. In that case also I think it will get cancelled up. So we can just, yeah, and there are other ways also of finding it out. I'll just talk about them. Now intensive properties are like, I've given you some good range so that you can remember. Surface tension and viscosity are again some kind of hot favorites. So temperature intensive, pressure intensive, not dependent on mass. Refractive index also you know. Then you have coefficient of viscosity, this is also independent of mass. Density is like mass by volume, so it's like a matter by matter thing. So here you have density and then you have specific heat. And let me just tell you some more things like characteristics. Note down some characteristics of intensive and extensive variables. There's no harm in noting it down. Characteristics of intensive and extensive properties. Now the first one is like, the product ratio or sum of intensive variables are intensive. The product, say if X is intensive and the other property Y is also intensive. That means, say if you have two intensive properties, then in that case the product X into Y, X by Y or X plus Y all will be intensive properties only. Like you have the combination of two, like mass by volume or something like that. Mass is extensive, volume is extensive, but mass by volume is extensive, by extensive it becomes intensive. So there are some generalized rules that I am talking about now. Another rule is that if you have X and Y to be both extensive, if your X property is extensive and your Y is also extensive, then in that case your X plus Y will be extensive, because the addition factor will not cause any cancellation, but X plus Y or dx by dy will be intensive. And there is another thing that you can talk about here. If X is intensive, and Y is extensive, then Y by X or Y into X or the differential dy by dx all will be extensive. And you can all check it for yourself, the same thing.
In the last question, in the third, if we are going to reverse it, x extensive and y intensive, then the result would be...
It's like one and the same thing. Like either of the two. If one property is intensive and the other is extensive, then the ratio of the two or the multiplication of the two will give you an extensive property only. Okay, I repeat the intensive and extensive properties again. Extensive properties are those which are independent upon the mass of the system or the quantity of matter contained in the system. And so whatever is related to your mass, matter will all be extensive in nature, like mass, volume, energy, heat capacity to begin with. Then intensive properties are the ones I and I. So intensive and I for independent. So they are independent of the matter of the system. So they are independent of the mass. So here we state that temperature, pressure, refractive index, then you have viscosity, surface tension, density, specific heat capacity are all intensive in nature. Now it depends, now you can also check up, like sometimes a question may come density and you may have forgotten as to what it means. So you know that density is nothing but mass upon volume. Now you know mass is an extensive property, volume is an extensive property. But from these rules you will get to know that if you have extensive by extensive, it will always give you intensive property. See, for the rest it's almost the same. If you check out the rest of the characteristics, you see that if both the properties are intensive, you add them or you take the ratio or you multiply them. It will give you intensive only because there is no scope of mass coming in. So obvious. So in the second thing, when both are extensive, you just have to remember that the ratio of extensive property by another extensive property will give you an intensive property. But the sum or the ratio, or the multiplication will give you the extensive only. Then for the if one property is intensive and the other property is extensive, then if one property is intensive and the other property is extensive, then in that case you have, remember that the ratio or the multiplication factor will give you an extensive property because one of them is now playing the role of introducing mass. It's also again obvious. The only thing that you can remember is like extensive by extensive gives you an intensive. Now a question has come up, why is pressure an intensive property? Why? Because pressure is nowhere related to the mass of the substance. If you are talking about the pressure, if you are talking about the pressure of the gas, it is mainly because of the collision of the molecules with the walls of the container. So I mean, it irrespective of what it is, it will just not depend upon the mass. It will depend only on the behavior as to how it is related to. And there are other factors also wherein you can actually in totality find it out. But pressure as an individual entity is independent of mass. Okay. So then next we move on to different kind of thermodynamic processes. Now depending upon which variable is kept constant, you can have different thermodynamic processes. Like there are 4 types that you must have done. Four types of thermodynamic processes, and those are: first one, isothermal. Iso means same, thermal means temperature. So this is that kind of a thermodynamic process in which your temperature is kept constant. So you all are very intelligent to make it out yourself from the name. And remember that whenever you're talking about the thermodynamic processes, it is always a process is said to occur when your state of the system has changed from some initial state to a final state. Otherwise, you say that the system is just as it is, then that would mean nothing at all. Then in that case, everything almost remains a constant. So, isothermal is the process when it is carried out in such a manner that the temperature remains constant throughout the process. Then you have adiabatic. Adiabatic process is the one in which heat is kept constant. So, and then the third one, isochoric.
Volume constant.
Alright, and then you have isobaric,
Pressure is constant.
where you have the pressure to be kept a constant. Remember that when I am talking about, say, isothermal, that means I am changing the system from one, so my P and V may be changing, but it is only T which is remaining constant. So in this case, the temperature from the initial to the final state is kept constant. Then for adiabatic, that means no heat is allowed to exchange between the system and the surroundings throughout the process. Because the heat can get exchanged, how can it get exchanged? Only between system and the surroundings. So in this particular case, you say that your dT is equal to 0. That the change dt is like, say, whenever you talk about macroscopic changes, you talk in terms of delta t. So delta t will be equal to 0 in terms of macroscopic. I mean, if you're talking about small temperature changes, say in that case, then you will refer to the differential form. So dt is equal to 0. In adiabatic processes, you will have your dq to be equal to 0, where q is basically the internal heat of the system. Then isochoric is the one in which the volume of the system is kept constant. Your pressure and temperature may be changing here, but the volume of the system is kept constant. An isobaric process is the one in which pressure of the system is kept constant. See, when you talk about any system which is kept open, when you talk about any system which is generally kept open, then in that case also you can say that that's an isobaric process, because you're referring to the pressure which is generally a constant. So that can also be referred to as an isobaric process. So 4 types of thermodynamic processes: isothermal, adiabatic, isochoric and isobaric. Isothermal, temperature; baric, pressure; choric, volume; adiabatic, heat. Then when you talk about the thermodynamic processes again, you can have 2 again demarcation depending upon whether the system can be reverted back or not. So then in that case you can have either a reversible process or you can have an irreversible process. A reversible one is the one which is carried out infinitesimally slowly, such that the rate of the forward reaction or is just infinitesimally, the driving force you can say is infinitesimally just greater than the force which can revert back the reaction, such that you provide a little bit of force extra and it can be reverted completely. That's your reversible process. And irreversible is something, the change that has been caused cannot be reverted back. So there are like good number of differences also in between reversible and irreversible that you can just take a note of. Reversible processes are the ones which generally occur slowly, and irreversible are the rapid exchanges. In this case, the opposing force and the driving force are just slightly almost equivalent. The driving force is infinitesimally greater than the opposing force in this case, but in this case the driving force will be much greater than your opposing force. Then you know that in this case the work done in a reversible process will be maximum, and the work irreversible is always less than the work which is done in a reversible process, because naturally the work that can be attained in doing reverting, first you using the driving force then you using the opposing force, will any time be greater than the work in the irreversible process. then I don't think anything more important is like mentioned here. Work done will be maximum in case of reversible process only, because what is a reversible process? That in which the reaction is going forward as well as coming back in the backward direction. So in that case it's like almost kind of a double the work in qualitative language. So you are like using the work done here. Work will be done to move in any direction. So anyways it's like an obvious thing. The rest of the points are like just elementary. Okay, so here we've talked about the different kind of thermodynamics. With this I think vocabulary is like, this is like what is by and large the vocabulary of thermodynamics, the terminologies that you should understand throughout. When I am talking about isothermal, the moment I say isothermal, you should immediately get the constant temperature factor. The moment I say adiabatic, it should be constant heat. So such kind of words need to be remembered. Reversible, irreversible is still something that you could have understood otherwise. But the only thing that is to be understood here, important points are that the work done in reversible process are always greater than, is always greater than the work done in an irreversible process. The rest of the definition is like what you understand by the meaning of reversible process. Okay, then next we talk about a concept which is known as internal energy. Now internal energy is now something which is known as, which is related to the energy of the system. Please understand this concept very clearly. It is like, say whatever system I talk of, it will always be associated with some energy. That is the energy that is possessed by the system itself. I am not doing any extra work, I am not snatching any extra work from here. So whatever, say I give you a system containing some kind of chemicals in it, okay, so that system, even if the chemicals are not interacting with one another, possesses internal energy. Clear with it? Now supposedly the chemical reaction happens, then only there can be some extra heat that can be absorbed or it can be given out. Then we will talk of something else. But as it is, when the chemicals were provided to the system, into the container, then in that case there was some initial setup in internal energy that was possessed by each of the systems. Like each one of you, unless and until you like poked, till that time you have some internal energy within you. So there will not be any exchange as it is. So one thing that you have to remember, unless and until you supply some heat changes to your system, the internal energy would remain constant. Remember that this internal energy, which is represented generally by U or E in some of the books. Some of the books also refer to the internal energy in terms of E. It is solely the energy which is possessed by the system. It is a function of temperature. So if your temperature is constant, remember that your internal energy will remain constant. Say if I have this, take my fist as a system. If I am talking about the system, naturally the meaning that I have told you, it possesses some internal energy. Now say the temperature is presently 25 degrees Celsius for this fist, okay, and if I heat it now, so what will happen? Then the internal energy will change, because naturally there will be some exchanges of heat, some thermodynamic process is happening now. But if at all I keep the temperature as constant 25 degrees Celsius without making changes, then in that case what happens to the internal energy? It will remain the same. So remember, if your T is constant, your internal energy will also be a constant. Not exactly, no. You can say that internal energy is dependent upon heat, but it's not a function of heat. When I'm saying it's a function of temperature, that means it will vary according to the temperature. And if you're keeping the temperature as constant, then your internal energy is also constant. But if you keep the heat constant and do some kind of work on it, then again internal energy will change. So it's not just a simple function of that thing. Okay, so I say that it is just a function of temperature. That's one thing. And this will also be doing as a part of the law. Please explain irreversible and irreversible processes again. Please write in big letters. I will write in big letters now. Now, reversible process is the one which can be reverted back. in which the driving force, say if I have any kind of reversible process, A plus B is becoming C plus D. If it cannot be reverted back, once your C and D are formed, if the process cannot be reverted back, then in that case I will call it an irreversible process. So in this case the driving force is much larger than the opposing force. But if my driving force is just infinitesimally greater than the opposing force, then in that case there is an equal probability of system to come back. So then in that case I will be calling it a reversible process. Reversible process.
Opposite force are much greater than the driving force.
In case of reversible processes, we say that the driving force is almost equivalent to the opposing force. Now what are you starting up with, A and B? So naturally the driving force is moving towards this. So driving force is infinitesimally, means very less, by a very less magnitude, will be infinitesimally greater by the opposing force, such that the reaction is proceeding in the forward direction, but at any point in time, the moment you move towards, it can always be reverted back. Then I told the last thing, an important point related to reversible and irreversible processes was that the work done in reversible process is any time greater than the work done in irreversible process. Okay. Now remember another thing for the internal energy. Say if I talk about the internal energy concept, remember that this internal energy is a state function. Now what is a state function? A state function is the one that depends upon the initial state and just the final state, and it does not depend upon the path followed. Okay, so U is kind of a state function, and you talk about any process and that process will always be associated with some or the other kind of internal energy. You talk about any chemical process and that process will always be related to internal energy. So basically this is the energy that is associated with the substance. Internal energy is the energy that is associated with a substance or system. And this internal energy is something which may be dependent upon the variable factors which are generally there. So after doing this, and if I am saying it's a state function, then in that case remember that state function means it depends only on the final state and the initial state. So if I want to find out what has been the internal energy change, it will be simply internal energy of the final state minus internal energy of the initial state. So you can also write it as U2 minus U1 if 2 is the final state and 1 is the initial state. The units of internal energy will be the same as that of the energy. So you can talk of in terms of joules or ergs or anything which is related to energy. Then when we talk about work, heat and energy, if I talk about work, heat and energy, we'll also be talking about the laws of thermodynamics in a short while. Work will always be the pressure volume work. Work is always denoted by some or the other kind of, say, intensity factor into the capacity factor. Work is always some kind of intensity factor into the capacity factor. Like for example, you have intensity factor, say force, and say work is also defined as force into distance. So remember that work is always represented in some kind of an intensity factor into the capacity factor, and your capacity factor is like volume and intensity factor will be your pressure. So you talk about the pressure volume work generally. Say whenever you talk of this generally refers to your mechanical work. This is your pressure volume work. And if you talk about, say, electrical work done, the electrical work is nothing but that's your EMF into the quantity of electricity. You talk about the gravitational work done. What is your gravitational work? That is equal to m into g into, that is your gravitational work done. So you can have actually different annotations for your work done. And when you talk about work done to be force into distance, or you can also talk about work done as force into distance, that can also be written as pressure into area. Alright, and that can also be, no, your force is pressure into area into distance. What is area into distance? That will be your I'll write it in big letters again. See, there are some important terms now to understand, to start understanding our thermodynamics. The very first one is that when I am talking about the work done here is some kind of an intensity factor into the capacity factor. So when I talk about the mechanical work done, it's force into distance that you've already done. Then we can talk about the other kinds of work done also, like the electrical work is your EMF into your quantity of electricity. Then you can also talk about the gravitational work, which is m into g into h. When you lay emphasis on your mechanical work, that is nothing but force into distance. What is your force? Force is nothing but pressure into area. And when you substitute it back into that work done expression, what do you get? That is pressure into volume. So if you're talking about the small amount of volume change because of the pressure, then in that case it becomes PdV, and when you integrate it, generally, and in the atmosphere the pressure remains a constant. So we take the total work done to be equal to, we take it in some form of minus P delta V. I'll just talk about the minus plus sign, but then you take it to be P delta V, where this pressure is essentially the external pressure. I want all of you all to remember that. Here this pressure that I am talking about is nothing but the external pressure. Right? External pressure means that if I have a container with a piston on top of it, then what will be the work done? It is like I will be putting pressure on the system. So this external pressure will be what is be counted here. Okay? Now if this external pressure is being put on the system, that means external pressure is being put, so it will be positive. So work done on the system is positive. But if it is expanding, if it is expanding means the work now, system is what? Whatever is within it is your system. So now if it is expanding means work, who is doing the work? The system. So work is being done by the system. So this pressure will be opposing your external one. So this will be opposite in the direction, so it will be minus P external dV. So you get the point that your work done by the system is generally negative and work done on the system is always positive. Why? Because the pressure that I am using in the formula is your external pressure. So get that thing. Right? Then you have, say you talk about the heat factor also, and when you talk about the heat factor, remember that the heat which is given by the system to the surroundings will always carry a positive sign. The heat that is given by the system to the surroundings will be positive, and the heat which is taken up by the system, absorbed by the system, will be negative. So it will be positive if it is given by the system to the surroundings. Alright, and it will be negative if it is absorbed. It will be negative. It is, if heat is given by the system, then it will be, I'm sorry, and if it is absorbed by the system, absorbed by the system means it's coming from the surroundings to the system. So heat gained by the system is positive and heat given from the system to the surroundings is negative. Sorry, so many notations are there. Remember these terms I don't know if I gave them to you before. 1 calorie is 4.184 joules, and you should remember the opposite the other way around also. 1 joule is equal to 0.2390 calories. Okay, something else that I also, you can also take up a question quickly and just answer it in a short while. The question is, calculate the amount of work done. Remember that you will just note down the important properties which are like given. So calculate the work done, so you have to calculate the work done, which will be minus P external dV, minus P external dV in for 1 mole of a gas, so N is equal to 1, contained in a bulb of 10 liters, so volume is given as 10 liters, at 1 atmosphere, so pressure is given as 1 atmosphere, and is allowed to enter into an evacuated bulb of 100 liters capacity. I repeat the question. Calculate the amount of work done when 1 mole of an ideal gas contained in a bulb of 10 liter capacity at 1 atmosphere is allowed to enter an evacuated bulb. Let me tell you, an evacuated one is the one which is in vacuum. So there is no kind of pressure thing there. Vacuum means there are no anything in it. So in an evacuated bulb of 100 liters capacity, so what will be the work done for it to expand from 10 liters to 100 liters? Can you see? Volume now is equal to 100 liters. So in this case, what will be the work done? You tell me. I will give you the options. The work done is 0, or it is 10 joules, or it is 150 joules, or if it is none of these. Now remember, it's like an easy question and I do not want you to waste time on it. In an evacuated chamber means that there is no pressure. So the moment you transfer your particular thing that of 10 liters, whatever that is, the moment you transfer it into the 100 liter capacity evacuated bulb, means there will be no external pressure. So it will be freely expanding. So external pressure will be 0. And if external pressure is 0, your work done will be 0. So remember, whenever there is kind of a free expansion, your external pressure will always be equal to 0. What did I say? Whenever there is kind of free expansion means your system can expand on its own. And if your system can expand, so what is the external pressure that is coming from the top? It will be 0, because अंदर से ही expand हो रहा है अपने आप, and that means if there is no pressure from outside, then in that case the work done by the system will be 0. Remember that the work done by a system will be said to be maximum only in case of reversible work. That also is something I am repeating again and again. Then here remember that whenever we talk of exact differentials, see there is something, I am just introducing it here so that you have an understanding for it forever, because this will be used in science always. You have something which is known as an exact differentials. You all do differentials, right? For the small, for any kind of small changes you talk about differentials. You put a limit and then you can finally come to the differentials. So you can have two kinds. You can either have an exact differential or you can have an inexact differential. Okay, now please pay attention to this. When you talk about differentials is any kind of small changes that you talk about. Here, when you talk about the exact differentials, means that there is definitely this change which is happening. Okay, and because you are talking about macroscopic properties here, you know that your thermodynamics is just talking about macroscopic properties. So when you are talking about the macroscopic properties, means you are talking about big changes. I mean the changes of big amount, which is a collection of different particles. So that will always be counted in terms of exact differential, which is represented by d by some dx or whatever variable you want to check it for. So this is known as an exact differential. Now whenever you keep one of the variables constant, now there is kind of an assumption. You know this, whenever you are keeping any of the variables as constant, then there comes in the idea of some kind of an assumption. So then it cannot be definite, that this is the property? Or in other words, just understand it, you talk of inexact differentials, the representation is like del here. So whenever you talk of inexact differential, that means that you are some kind of an assumption that has been put in, or some variable had been kept a constant. When you assume something, then you know that the answer that you got may not be 100% correct. So it may not be exact. So what will it be? Inexact and or otherwise. So that is why when you do, you have already done atomic structure with me. Whenever you do quantum mechanics, what is quantum mechanics? Microscopic particles. So whenever you do quantum mechanics, there you always talk of inexact differentials because there is a probability related. It may or may not be there. It may be present, or this is just a probability. Probability means chances hai. So that ways you talk of inexact differentials. So you get the difference between exact differentials? Inexact differentials is like, for example, when you talk about, say, I am talking about some variable x which is dependent upon just T and V, and your pressure is kept constant. So then in that case, whatever value I am calculating will be kind of an inexact. Okay, so there I would be talking of del by del T. So the moment you see this, do not just get worried, because the differentials carry the same meaning. Del by del x means the first derivative. Del square by del x square means the second derivative. The meaning and the formulae are just the same. Del only indicates that this is inexact in nature when you have kept any of the variable as a constant. So then in thermodynamics you can talk of inexact. Otherwise, you know that thermodynamics always deals with macroscopic entities, and your macroscopic entities are for larger, and whenever you talk of larger things, you can always talk about the exact differentials when you are absolutely sure. And the moment you move on to the quantum, there you will always be talking about inexact differentials. So this was one thing that I wanted to lay emphasis on. Okay, so now here, next we move on to say state and path functions. Before state and path functions, I want to give you one more question. Not given here. Okay, just now state functions and path functions. Remember that state functions are those which are dependent only on the initial and the final state. What is EMF? EMF is electromotive force, and it is expressed in volts. Okay, and one more thing, the question is what is EMF? EMF is electromotive force, and it is some kind of a potential which is expressed in volts. Then why a force? Force is electromotive force is what you are saying, and it is representing your potential, which is voltage in volts. Remember, it's a misnomer. Misnomer are certain words which are assigned to the term, but otherwise the meaning is different. Alright? There are many more terms which act as a misnomer. So not just this one, it's like a general terminology. So electromotive force. There was another doubt? That was the only one? And the path functions are those which are dependent on the path followed. Like for example, we have say Q and W to be the path functions, and your internal energy is generally a state function. So that means U will be dependent upon only U2 and U1, and your Q and W will depend on how it has been, how has it reached the final thing. Alright, now there are two more formulae that I want to give you. One is the coefficient of thermal expansion. Coefficient of thermal expansion, because we have a long class tomorrow, so we'll do all the questions based on it. So just be thorough with the formulae. We have the coefficient of thermal expansion or expansivity, that's alpha, and it is given by the formula of 1 by V. It is given by the formula 1 by V into del V by del T at constant pressure. Now you get it?
Yes, ma'am.
So because it is pressure, so that is why it is given as del and del. Otherwise, if you find it in books as 1 by V into dV by dt at constant P, it is just the same. This is then not an exact differential but an inexact only. So this is only a representation where your pressure is kept constant. So then if any of the variables is kept constant, means that you are talking about inexact differentials. So alpha is the coefficient of thermal expansivity or thermal expansion, which is given by 1 by V into dV by dt at constant P, whatever way you are comfortable in memorizing. It is dV by dt at constant P, and there is a coefficient of compressibility also. There is a coefficient of compressibility which is beta, and it is given by minus 1 by V dV by dP at constant T. Okay, so the only change is in one pressure is constant and the other temperature is constant, and your compressibility has a minus sign. So memorized, coefficient of thermal expansion is 1 upon V dP by dV at dV by dt at constant pressure, I am sorry, and then for compressibility coefficient you have, that is minus 1 by V dV by dP at constant temperature. Remember, in thermal expansion your temperature is constant, and in your compressibility coefficient, sorry, in thermal expansion your volume is constant. Thermal means its expansion due pressure is constant. In your thermal expansion, what I wanted to state was that the expansion is due to thermal change, due to heat change. So due to heat change, that means now your change is with respect to temperature. So in that case, I repeat, coefficient of thermal expansion is 1 by V del V by del T at constant pressure. Okay, now no confusions. And then the compressibility coefficient beta is nothing but it is the now the change with respect to your pressure, because compression or expansion is all because of pressure. So that means your pressure will come in the denominator and you are checking the change in volume. So it is the change in volume with temperature in thermal expansion, change in volume with pressure in compressibility coefficient, and the other third factor is constant. Clear? Okay, calculate, there is a question, calculate alpha and beta for an ideal gas. Calculate alpha and beta for an ideal gas. Now how will you solve it? I'll quickly do it for you. Remember that PV is equal to RT for 1 mole of a gas. Now if you take up, differentiate this equation, if you differentiate, on differentiating, what you get is, pressure is like constant for alpha. Pressure is constant for alpha, and remember that whenever you have, please look up here, if you have to differentiate dPV with respect to T here, alright, dPV with dt. So I take dt to the other side then in that case, if you have to cause about any change, it will be PdV plus VdP. Please remember this, it will always be, I don't know if you've done all these rules, so your differential of PV will be nothing but PdV plus VdP. So then in that case, if I am keeping my pressure constant, then in that case this dP will be 0. So it will be only PdV then in that case. So here what I have is PdV minus VdP is equal to R into dt. Do you get it? It will be, I am doing d by dt of PV. Then I am taking what will be d by dt of PV? Here on the right hand side it will be simply R, and d by dt of PV will be your, the numerator will become PdV minus plus VdP, and you are taking dt on the other side. Clear with this term?
Yes, ma'am.
So here next you have you take dv plus dv by dt will be at constant pressure will be equal to r upon p. Now dv by dt at constant pressure, dv by dt at constant pressure, so constant pressure this goes off, so dv by dt will be equal to r upon p. Did you all get it? Simple. Now what do you have to do? What is your alpha? Alpha is 1 by v dv by thermal expansion with respect to temperature at constant p. So what is your dv by dt at constant p? R by p. So that will be nothing but r by pv. And what is your pv equal to? For 1 mole RT. So this will be equal to 1 by T. So you check the options, whichever option is like given. If it is like in terms of RP or T or whatever, you can just always do it. So remember, alpha for an ideal gas is equal to 1 by T, or else you can just directly remember. Then calculate it for beta also. For beta, now what do you have to do? The same equation can be used. Now you check up for dV by dP at constant T. So this term will go off and dV by dP will be equal to minus V by P. Do it quickly and tell me what will it be. I hope I won't have to repeat it, so please look at it again. Alpha is the coefficient of thermal expansion. That means it is some change of volume with respect to temperature. So the expression is 1 by V dV by dt at constant pressure. Then we talk about the compressibility coefficient or the coefficient of compressibility, where we are talking about the change of volume with pressure. So that will be minus 1 by V dV by dP at constant temperature. Alright, and now the question is to calculate alpha and beta for an ideal gas. Alpha, you know, we need this term basically, dV by dt for an ideal gas. We will calculate PV is equal to RT is what we know. We have written down the equation by taking d by dt for this case. When we take d by dt, we get this expression at constant pressure, we get R by P. We just substitute this expression back into our alpha to get the final answer as 1 by T. Clear? Now when you do it for beta again you have to use PdV plus VdP is equal to RdT, and there now you get dV by dP at constant temperature. So if you keep temperature constant, your RHS will become equal to 0 and your LHS will be equal to your VdP plus PdV, that will be equal to 0, and then you can calculate your dV by dP. So what is the final answer for beta? For alpha we got it 1 by T, and for beta it will be 1 by P. So remember, for ideal gas your thermal expansion in this case will be T inverse, and for this case it will be P inverse. Easy to remember also. And Joule's mechanical equivalent of heat is the one in which the work done is directly proportional to Q, and this is Joule's mechanical equivalent. You say that this is the Joule's mechanical equivalent of heat, where this will be introduced as J and your work done will be equal to J into Q. This is another expression for work done. Remember that your work done is directly proportional to the heat. So when you remove the proportionality constant, you get the coefficient, you get the proportionality constant here. When you remove the proportionality sign, this J is known as the Joule's mechanical equivalent. This is known as the Joule's mechanical equivalent. That is, if Q is equal to 1 calorie, you know that work done will be equal to the Joule mechanical equivalent. So Joule's mechanical equivalent is basically defined as, Joule's mechanical equivalent is defined as the amount of heat, the amount of work required to produce 1 calorie of heat. 1 calorie of heat. It is the amount of work required to produce 1 calorie of heat. This is just an expression that you need to remember. Then we move on to the laws of thermodynamics. Now finally we start up with our main work after discussing all the terminologies. What is the first law? That not the first. Now normally to begin with, the 0th law of thermodynamics, which is no, I am talking about the 0th law. 0th law. When I said first, I stopped because the first law of thermodynamics is something else. To begin with, we talk about the 0th law of thermodynamics, and it states that if two systems, say if A and B are two systems which are in equilibrium with a third system, alright, if A and B are two systems, C is another system. If A and B are two systems which are in thermal equilibrium with a third system, then A and B are also said to be in thermal equilibrium with each other. I repeat, simple, very simple. Look up, we are talking about three systems, okay? 0th law of thermodynamics states that if two systems are in thermal equilibrium with a third system, then these two systems are said to be in thermal equilibrium with each other. Obvious thing, okay? So you can repeat it also. What does 0th law states? It states that if two systems are in thermal equilibrium with a third system, two systems are in equilibrium with each other. Okay? That is what your 0th law of thermodynamics is all about. And when you are talking about the thermal equilibrium, you are essentially talking about what factor? Temperature. Okay, then we talk about now the much awaited one, the first law of thermodynamics. This is nothing but the law of conservation of energy. That is, energy can neither be created nor destroyed, but it can change from one form to another. This is your first law of thermodynamics. What does it mean? It means that the total energy of the system remains a constant. It is equivalent or the same as your law of conservation of energy. Law of conservation of energy. So what we have in it is that energy can neither be created nor destroyed. So what does it mean? It means that the total energy of the system remains a constant. The total energy of an isolated system, sorry. How can a total energy of a system remain constant? Only when there is no exchange of energy and matter. So the terminology is very important. It means that the total energy of an isolated system that remains constant. The mathematical expression of the first law of thermodynamics is that change in that delta U is equal to the change in internal energy will now depend upon the heat of the system plus the work done. Alright? It is nothing but the heat done at the system plus the work done. And remember that I told you internal energy. This is your internal energy. We've already talked about these terminologies. Your work is minus PdV, where P is your external pressure. It's basically your pressure. So now external pressure, and you have when work is done on the system, it's positive. When work is done by the system, it's negative. When heat is given by the system to the surroundings, it's negative. When heat is absorbed, it is positive. Your delta U will then depend upon Q and W accordingly. The magnitude of your Q and W. It also states that the change, it can either be written like this, or it can also be written as dQ is equal, your du is equal to Q plus W can also be written like that. Right? And now, when we talk about the cyclical change, when I talk about the cyclical change, remember that you're in a cycle, what happens? In a cycle, if I am talking about the starting from here, it will come back to the same point again, and your internal energy depends upon the initial and the final state. So your cyclical change of internal energy will always be equal to 0, or for an isolated system it will always be equal to 0, which would imply that dq plus dw will also be equal to 0, which would imply clearly that your dq plus dw will also be equal to 0. So now if I give you a question here, if I am giving you 3 graphs, sorry, not a closed one. If I give you 3 graphs of pressure volume, you know that your pressure and volume, whenever we talk of pressure and volume, we are talking about the work done by the system, right? And let me just talk about the system moving from one state to another, and I'll give you 3 options. You have the system moving from state A to state B. These A and B are same in all the graphs, A and B, alright. In one case it's moving like this, in another case it's like moving this like this, and in another case it's moving like this, alright. So in which case your internal energy will be the maximum. Now the question is, the internal energy is maximum in, say, option A, B and C. The options are, the internal energy is maximum in A. No, which of the options is correct should be the question. The internal energy is maximum in B, or small a, small b, or the internal energy is maximum in C, or the internal energy is same in all, is the question. I repeat it again. I repeat it again. I am talking about your internal energies, which will be like your system is moving from point A to point B. This is giving you the pressure volume work done, alright. So you get an idea about the work done. In this case, the work is being done in such a fashion that the system is moving from A to B like this. In this case, your system is moving from A to, say, some point and then taking a right turn towards B. In this case, it's moving straight first and then moving down towards B. The question is, which of the following statements is correct? The first one, the internal energy is maximum in A. Second, the internal energy is maximum in B. Third, the internal energy is maximum in C. And the last one, it is the same in all. It is the same in all because it depends upon initial and it is independent on the path followed. So irrespective of what path is being followed, if the initial and the final points are same, then the internal energy will remain the same. Okay. So what is the mathematical expression? du is equal to dq plus dw, or delta u is equal to q plus w. That is your mathematical expression for the first law of thermodynamics, asked many a times. So then remember that your work done is equal to minus P delta V, and you know that Q is equal to delta U is equal to Q plus W. What is your first law? Delta U is equal to Q plus W. So what is your Q? That is equal to delta U minus W. So then in that case it will be delta U plus P delta V. Then it will be delta U plus P delta V. Alright. Now if I am taking, what am I taking here? Pressure to be a constant. Now I want your attention onto the board quickly. Look. We know that this is a path function. U is our state function. This is the information that we have till now. This is like we are keeping the pressure constant. Otherwise we would have had another expression V delta P also. We are not taking that expression. We are taking the pressure to be a constant, which means it is the heat at constant pressure. Whatever quantities we are talking of, they are all at constant pressure. So this means that my U will be nothing but it will be U2 minus U1, final state minus initial state, plus, I want your attention here on the board, plus P into V2 minus V1. Okay. Now if I just rearrange this expression, I get all the final terms together and I get all the initial terms together. So I get U2 plus PV2 together minus, I can put in the brackets now, U1 plus PV1 together. Now here there is another thing to understand. Look carefully, that means my internal energy plus this pressure volume factor. In together this is your final state, and in together this is your initial state. So there is some factor again which is dependent on my U and PV, which is getting added up in this fashion, which depends only on the final and the initial term, and this is some internal energy that was possessed by my system plus the pressure volume thing that was coming because of the work done at constant pressure. Getting? So internal energy plus your PV can now be introduced as a new state function. That state function can be summed up as, can be called as H, which is your enthalpy. Now this is your enthalpy, which is also a heat. It is a kind of heat, which is H2 minus H1, and that will be your QP. So remember that how can you relate your enthalpy to the heat that was involved in your first law, because this confusion remains throughout. This is the heat that is responsible for your internal energy. When you talk about this heat at constant pressure, it is the same as your enthalpy change. Get the point?
Yes,
so here your H2 minus H1 will be your delta H now, and we have now introduced a new state function. It automatically has come as a state function. Internal energy is what we understood as a state function. First we defined it, then we understood it's a state function. Now using the concepts, we are now getting that we here have some kind of a factor which is dependent only on the final and the initial state. And what is that? U plus PV. And that will be called as enthalpy now, which clearly indicates that your new term enthalpy is H is equal to U plus PV. And it's a state function. So you get the definition of enthalpy also from the first law. Remember that your H is related to the first law. Internal energy also comes from the first law when you define it. Okay. So we have time. We can quickly move on to the next term. Basically, as you noted down, I'll just read it out for you, that your enthalpy is nothing but the energy stored within the substance or the system, that is, it is the energy that is stored within the substance that is available for conversion into heat. It is that energy which is stored into the system that is available for conversion into heat. Now say what is your U? U is dependent on Q and plus W. And what is your this PV? It is the extra work done. So that adds up to the enthalpy factor now. And if you have to relate it to Q, your Q at constant pressure is nothing but your delta H. Let's move on to the factors which are more important. Let's talk about the heat capacity after this. I would have given you a numerical on enthalpy, but you will take time. So, clear? Now the 0th law was the one which talks about the three systems to be in mutual equilibrium with one another. When two are already in equilibrium, those two will be in equilibrium with each other. Then the first law of thermodynamics is the law of conservation of energy. The mathematical expression for which is delta U is equal to Q plus W. Then from here, when we take it constant pressure, we then introduce a new concept which is nothing but U plus PV, which is nothing but your enthalpy, which is again a state function. That till here it's clear to everyone. And that enthalpy delta H is nothing, the change in enthalpy is equal to your heat at constant pressure. That heat is contained in your internal energy factor, so you can always relate it to that. And your H is internal energy that is contained in the system plus the extra PV. So remember that enthalpy will always be greater than your internal energy. And what is your internal energy? Something which is stored in your system already. Okay. just the qualitative meaning of it. Now we've already discussed heat capacity in our gaseous state once. Did I? Heat capacity is the amount of heat required to raise the temperature of a substance by 1 degree Celsius. Your specific heat is for 1 gram of a substance by 1 degree Celsius. Your molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a substance. Very, very good. So when we talk about heat capacities now at constant volume, I told you heat capacity at constant volume will be dQV by dt. It is the amount of heat. What is your heat? Q, heat of the system बोल रहे हैं ना. So it is the amount of heat required to raise the temperature of the system by 1 degree Celsius, means per degree rise in temperature. So what is your QV? Your dQV is nothing but, you have your, that will be equal to your du by dt at constant volume. Your du is nothing but your Q at volume. Why? I did not tell you that, but your du is equal to dq plus pdv. dq plus dw होता है ना. फर्स्ट लॉ क्या है? फर्स्ट लॉ इज du is equal to dq plus dw. Your dw pressure, we take it to be the pressure volume work, which is pdv. Now if your volume is constant, then your du will be equal to dq at constant volume. So when you are talking about the heat capacity at constant volume, it becomes equal to dqv by dt, which is nothing but du by dt. And similarly, if you have to define the heat capacity at constant pressure, that will now be heat capacity at constant pressure क्या होगा? Cp. Cp is equal to the amount of heat required to raise the temperature of the substance by 1 degree Celsius at constant pressure. What is your dQp? We just saw when we defined enthalpy. Qp is nothing but your dQp is nothing but it is the change in enthalpy, so it will be dH by dt at constant V. Constant. I do such frivolous mistakes very often. I should stop that. Okay, so Cv is equal to dQv by dt, you know the meaning. Cp is dQp by dt, you know the meaning. Just remember, Cv will involve internal energy du by dt and your Cp will involve dH by dt. ये major difference है between Cp and Cv. You should know this because you know that Cp minus Cv is equal to, this is something that we've done in gaseous state. Another thing is like Poisson's ratio. Was this the name? So that is Cp by Cv is equal to your gamma. And I am not telling you how to calculate it again. That was the whole law of equipartition of energy and then degrees of freedom and all that. So you know that it is like a value that is known for monoatomic gases, for diatomic gases and triatomic. So you should, I did tell you that you should remember the values also. What are the values for monoatomic, diatomic? You need to give the test also for this. For monoatomic it is 1.67. At least remember for the monoatomic. For diatomic it is around 1.4. For tri I don't remember. So but please remember, for tri it is like I think 1.28 or 1.3, something like that. So it's easy, 1.67, 1.4 and 1.3. Will you remember now? Roughly, please check the exact values. So here we are talking about the heat. Okay. Now there is another very important concept that needs to be done. Please go through all the formulae that we have done today. Please go through all the definition and all the formulae that we are doing today. Now see, let's talk about the changes in Q, W, delta H and delta U, because these are the terms that we were introduced to till now. We've done only the first law. Let's talk about two processes only. To begin with, let's talk about the first process, which is like isothermal processes. Let's talk about the isothermal processes. Now what does isothermal processes means? That your temperature is constant. I want your attention onto the board. Stop writing now. ठीक है, because this is like important that you should remember. When you talk about processes, there are by and large two types of processes. One is a reversible process and the other is an irreversible process. ठीक है, reversible process and an irreversible process. Now reversible, so it's okay because in that your internal pressure would be almost equivalent to your external pressure. Then there will be some kind of a reversible factor introduced, right? एक container I am talking about a piston, imagine करो. So then in that case your external and internal pressure will almost be the same. Now for the irreversible there are two cases again. One case is where you can have intermediate expansion. Let's talk about expansion processes only. Okay, expansion means work will be done by the system. So intermediate expansion, intermediate is where the pressure has some value, where the external pressure will have some value. And let's another one be the free expansion. So that is also irreversible. Free expansion means it will not be reverted back. So that is also an example of free expansion. Now let's talk about generally the isothermal process. We have to calculate these terms, the expression for these terms. So here, if temperature is constant, you tell me what will be delta U. Generally, I told you while introducing internal energy, it is a function of temperature. So if the temperature is constant, your U will also be a constant. So your delta U will be equal to 0. Clear with this? So your delta U will be equal to 0. Another thing that I want to tell you here is that if your delta U is 0, what is your delta H? That will be delta of U plus PV. ठीक है? We are talking about the reversible isothermal expansion of an ideal gas. Stop writing. I'll give you the formula again tomorrow in the morning only. We'll meet. So reversible process is like something, we are talking about reversible isothermal expansion. First of all, isothermal expansion pe let's lay emphasis. Isothermal means constant temperature. Temperature constant means our internal energy is constant. So delta U will be equal to 0 throughout. So say it be this case, this case, this case, delta U will be equal to 0. So let me just put it. Here delta U will be equal to 0. Delta U will be equal to 0. Here also my delta U will be equal to 0. Clear till here? Then delta H, let me just find out delta H. If delta U is equal to 0, then obviously delta U is equal to Q plus W. So naturally your Q will be equal to minus W or W will be equal to minus Q. So that's like the relationship that will be there. But what is your H? H is equal to U plus PV. ठीक है? Now delta means it's the difference between the two states. So delta H will be equal to delta U plus delta of PV. Now what is your delta U? It is 0. PV for an ideal gas is equal to 1 mole RT or n number of moles also. So RT means R is a constant, I take R outside. R delta T. What is your T? It's a constant. So it is 0 plus 0. So delta H. So for the moment it is said it's an isothermal process. Reversible, irreversible, expansion, compression, whatever. Your delta U will be 0 because U is a function of temperature. You get many questions based on this. Your temperature will be constant, all the other values will be given in the numerical. But your internal energy will just be 0. Remember, temperature constant means internal energy is 0. And if your internal energy is 0, then for an isothermal process, your delta H will also again be equal to 0. So delta H is equal to 0 and again delta H will be equal to 0. Ye to common things ho gaye. So now let's talk about my Q that will be equal to or W that will be equal to minus Q, whatever you want to write. Now what is your W? W is equal to minus P external dV. ठीक है? What is your W? It is minus P external dV. Now if I talk about W to be minus P external dV, here P external means the external pressure. अगर मैं रिवर्सिबल प्रोसेस की बात कर रही हूँ तो माई इंटरनल प्रेशर विल बी इक्वल टू द external pressure. That means I can replace it by the pressure of the gas which is inside my container. ठीक है ना? That is P gas into dV. What gas is this? Ideal. So this can be replaced by my ideal gas law equation formula. So PV is equal to RT for 1 mole. So it will be RT by, so this becomes equal to minus RT by V, minus RT by V. So, sorry, this will be dW of course because I am talking about the small amount of work done. I have taken dV here. ठीक है? So, if I want the complete work done, I will be integrating it. ठीक है? What is the integral of dV by V? It is natural log of V. It is ln of V. dV by V is nothing but it is ln of V. All of you all know that. And what will be the limits? My volume is getting expanded, say from V1 to or V initial to V final. So then in that case I will get this to be equal to minus RT ln of V2 by V1. Doesn't give here. And if you remove this ln sign into natural log, into log to the base 10, then you have to multiply it with a factor of 2.303. So that will be equal to 2.303 RT log, minus is also there, log V2 by V1. Now this V2 by V1 can also be changed with pressure. So you can change it accordingly. You know that pressure is inversely proportional to V. So it will be P1 by P2. So please put down this expression. Now quickly, for isothermal reversible expansion, first of all, here we have internal energy to be equal to 0. Why? Because temperature is a constant. Here it is a function of temperature. Then delta H is equal to 0. I have explained it on this side. Delta H means delta of U plus PV, which means it will be delta of U plus delta of PV. For an ideal gas, PV is equal to RT. So it becomes delta U plus R delta T. Delta U is already 0. Delta T is a constant, so that also becomes equal to 0. So your enthalpy change will be equal to 0. So two things which are common throughout for an isothermal process is that delta U will be equal to 0 and your delta H is also equal to 0. Now, then according to the first law of thermodynamics, if delta U is equal to Q plus W, so if delta U is 0, your Q will be equal to minus W. For a reversible process, if I check up the formula for dW, it is minus P external dV. ठीक है? And in this, my external pressure can be replaced by the pressure of the gas because they are similar. Reversible है ना? So they are similar. So if I am replacing it with the gas, only then I will get this to be equal to, I am writing this because you have already done it. Otherwise, I would have straight away given you the formula. It gives you a better understanding. So you have RT into dV by V. So when you integrate it, you get minus RT ln of V2 by V1. That's the expression that you need to remember for the work done for an isothermal reversible process. If you remember work done, Q will automatically be known. ठीक है? और अगर ये V2 by V1 है तो P1 का, so pressure will be P1 by P2. So remember the final expression is important for you. Now let's talk about this. Quickly look up here. What will be the change in enthalpy when a solid melts? We'll talk about it. Let me just complete this particular process first. Ma'am, please, how to convert ln into log? See, ln of x को अगर log में convert करना है, that will be equal to 2.303 into log of x. This log is to the base 10 and ln is normally to the base e. So minus RT ln of V2 by V1 can be written as minus 2.303 RT log of V2 by V1. Alright. Next, what we have here is, we talk about the irreversible processes now. And when we talk about the irreversible processes, remember that here in case of irreversible process, you have to calculate again your W. Q will be equal to minus of W only. What will be your W here? dW will be minus P external dV. अब इस केस में ये irreversible है, तो whatever your external pressure is, it's different than, much different than the pressure of the gas, so we cannot replace it now. So in that case it will be simply you integrate it and you integrate your dv. What is the simple integration of dx? It's x. When the limits are v1 to v2, it will be v2 minus v1. So the general expression for the intermediate expansion, it will be minus p external v2 minus v1. बाकी की terms you already know. ठीक है. Now for the free expansion, dw is equal to minus p external dv. Free expansion means what is your external pressure? 0. So in case of free expansion, your W will be 0, so Q will also be 0. So remember, whenever you talk of free isothermal expansion, everything will be 0. Intermediate means that some external pressure will be there. Yeah. And that external pressure has a value which is much different than the pressure of the gas. Okay. Then here, now we summarize all the formulae. Remember, now if you are talking about the isothermal processes, in isothermal processes your delta T is a constant. If your delta T is constant, सबसे पहले delta U will be a U will be a constant, that means delta U will be equal to 0. If your delta U is 0, then your delta H also becomes equal to 0 for an ideal gas. Then we have to calculate now the work done. So the major thing that is left in different types of processes is that the work is, we need only to calculate the work done. So what will be the formula of work done? It will be, you have to remember, minus 2.303 RT log of V2 by V1. Will you remember that? That will be equal to minus 2.303 RT log of V2 by V1. Alright. Now for an irreversible processes, we have two types of processes: intermediate expansion and free expansion. Free expansion, everything is 0. And intermediate expansion, now your work done is minus P delta V. That is minus P delta V. That is simply minus P delta V. So the only expression now that you need to remember is for the reversible isothermal expansion. And remember, if you know the work done, your Q will be minus of that particular work done. So it will just minus sign and it will be changed. So whatever is asked in the question, read carefully, work out for the work done, and then mention it as Q. We'll do lots and lots of questions based on it tomorrow. One thing that we are now left with is adiabatic processes. Now all these terms will also be, we'll also study them for the adiabatic, reversible and irreversible processes, and from here we'll start tomorrow and take up the thermochemistry as well. Thank you very much.